Hi, in this video, we're going to take a look at path analysis. Now, this is going to be the first video on path analysis and structural equation models. And so as a first introduction to this, we're going to approach a simple path analysis model using linear regression. So this is the simplest structure that we could possibly have for a path analysis model. And we're basically going to just work through it. We're just going to do everything the linear regression way. So that way, we get a more natural feel because regression is so well known, so well established and covered in so many courses. All right, so we're going to be working through an example from Modern Psychometrics with R by Mayer, and here is the website on GitHub to get the code. Now, I've modified the code to present things the way that I feel, it just make it more similar to how I like to code, honestly. And then I also expand on a few points here and there. All right, so first thing I want to talk about is the difference between multiple linear regression and multivariate linear regression. All right, so if I have multiple regression, what we have is that we have multiple independent variables, but we have one dependent variable. All right, so multiple linear regression has one dependent variable. Now, if I do multivariate regression, once again, we have multiple independent variables, but we have multiple dependent variables. And this is how we're going to approach our first simple path analysis model, is that we're going to have multiple dependent variables, which will be the factors that we're interested in. All right, so there's three ways of computing multivariate regression models. First one is to use classical linear models context. So here we're doing like linear algebra, and it's just a very natural extension of the linear algebra from a simple linear regression course. Next one is to fit the model through a path analytic framework. And then next one is to use mixed effects models to specify random effects for the random variables. All three will work for our purposes. We're only going to look at the first two. The first one, we're basically going to approach everything from a linear algebra extension to a multivariate regression. And then after that, we're going to use the path analytic framework, and we're going to work through fitting it in a different manner, in a way that is consistent with the psych package, or excuse me, the LeBlanc package. All right, so for our data, what we're going to do, we're going to use the data set from Berg et al. Once again, and we're going to be modeling two types of prejudice using agreeableness and openness. So we're going to use, I think, if I remember correctly, we're using ethnic prejudice and prejudice towards people with mental disabilities. And our indicators, so those two that I just mentioned, the two types of prejudice, are factors. They're latent variables, so we don't directly observe these. But what we do see are measurements of agreeableness and measurements of openness. And we're going to measure both of the latent variables with those four indicator variables. Okay. So let's go ahead and load the data. And I'm setting the options down to 2 digits just so I don't get blasted in the face with numbers. And then we're pulling the data from the MPsycho R package, which is the R package that is a companion to the textbook. And now let's go ahead and actually do multivariate regression this way. All right, so you'll notice that I'm actually using standard linear models. That's surprising, huh? How I do this, and the trick to this, the data is the same with regular, simple linear regression or multivariate regression. The formula is very similar, but here I put C-bind around my dependent variables like that. And I just run it as is, and I get the results. So now, once I have the model built, I want to do ANOVA, right? Well, I don't quite do ANOVA. I do MANOVA, multivariate ANOVA, right? Very natural name. And we're using the CAR package to work this out. And so here we can see that This looks like it's not adding as much as we would like, but these three are definitely statistically significant. Okay. And so remember, this is a type 2 MANOVA test, while down here, this is going to be like a type 3 ANOVA working out. So if I look here, we're looking at just the ethnic prejudice model. Remember, we have two models coming out of this. So ethnic prejudice is the one that we're looking at. We see that the intercept is statistically significant. We see that second agreeableness and both openness are statistically significant. But here we can see that agreeableness 1 is not statistically significant. Okay. Now we can look at our diagnostics just like we do with regular regression. We notice that the R squared is less than we want it to be, but the model overall is statistically significant, which means that there is something good in there. It doesn't tell me what is good. It just tells me that I have useful, informative predictor variables somewhere in there. That doesn't mean all of them are informative. Now, if I do the summary on the prejudice towards people with mental disabilities, we can see that we get similar results, that the intercept and the second agreeableness and both openness are statistically significant, but the first agreeableness is not. Okay. And once again, we see that our R squareds are definitely less than we want, and that our p-value shows that we have something good going on here. So there's something interesting, something worth digging into. All right, so now let's approach things through the second manner. So here, I want to use the Lavon package. So Lavon stands for latent variable analysis. And here I'm going to specify my model. All right, so check out this model. We're saying that ethnic prejudice is dependent on agreeableness 1, agreeableness 2, openness 1, openness 2. Prejudice towards mental disabilities depends on agreeableness 1, agreeableness 2, openness 1, and openness 2. Now the terms here, I choose what those look like. I choose what to name them. And so I put the target variable or the dependent variable and the independent variable matching together. That way, when I look through the output, it's easier for me to know which coefficient I'm looking at, because I've got two equations, and you'll notice that in each of the equations, I'm labeling the coefficients with the target variable and with the predictor variable. That way I know which pair I'm looking at each given time. Okay, so now once I get the model built out using SEM, I want to get a feel for what's going on. So I go ahead and I use the structural equation modeling paths. And here we can see the results. All right, well, I see I've got negative, 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 and that's really small. And so, and notice the arrows. The arrows having just one head indicate like the direction of the dependent independence. Now, when I look here, the double head arrows, that indicates a covariance relationship. And so we can see that throughout. So the equations that we're really interested in are here, and these parts are, these double head arrows are evaluating the covariance of residuals aspect. All right, so here, let's go ahead and take a look. Now, what I'm going to do, I'm going to do a little bit of data prep to arrange things so that it's a little bit easier to interpret and to visualize what's going on. So if I take the Lavon package parameter estimates, it's going to put the left-hand side of an equation in one column, the operator in the equation in a column, and it's going to put the right-hand side of the equation in another column. Well, for my purpose, I want it all in one spot. So I go ahead and I run a paste command, and I put the three of them together. Left-hand side, operator, right-hand side. That way everything works out nicely. Now, in a moment, I'm going to plot confidence intervals. Now, when I do that, I want things to be ordered in a manner that it's easier for me to read the displays, read the plots. So I'm going to use a factor command to sort things, to sort the formulas by the estimated values. That way it's easier for me to evaluate what's going on with each of the confidence intervals. And here I reorder the columns just so it's a little bit easier to interpret what's going on. All right, so now let's look at the manifest coefficients. Or actually, this should be regression coefficients, but okay. And so here are the estimated coefficient values. Here's the standard error. Here are my confidence intervals, z-score, p-value, and the labels. All right, and the labels correspond to the formula that I specified above. All right, well, that's a lot of numbers, right? It's hard to interpret these numbers as I look through them. I can pick and choose, but it's just easier to make it into a picture. So I'm going to use ggplot with geom error bars, and I can see that these two here include 0 in the intervals, while these do not. All right, so maybe I should reduce these. Let's see, what is this? Or agreeableness 1, agreeableness 1. In both models, the coefficient confidence interval includes 0. So I might want to remove those. Now, my personal opinion in regression is that it's okay to have, under most circumstances, it's okay to have one one independent variable that is not statistically significant. The reason why I say that is because if I'm working to reduce my model down, I find that not allowing any non-significant independent variables tends to be too harsh of a criteria for model building. So I usually allow just one, and that's good. So here, I've got one that's not statistically significant in each model. So I'm satisfied with this model as is. So I'm feeling good. Now let's take a look at the covariance of residuals. And I can see that we do not have 0 covariance anywhere for our confidence intervals. And so what this is, what this is telling me is that the residual covariances are not independent, or excuse me, do not have 0 covariance with respect to DP and EP. All right, so if you think about regression, remember that in regression, we always, to be able to do our full analysis, to be able to trust all of our p-values and all of our interpretations, we need to have constant variance with respect to our predictor variables. All right, well, we clearly do not have constant variance. So, but here it's with respect to the target variable. So that's something to think about. Now here, I'm going to look at the residual covariances with respect to indicator variables. And it's very similar. Now, something about this, if I look at the table, so here I'm looking at the residual covariance for each of these, and you'll notice I get estimated values, but every single time I have standard error equal to 0. Okay, so that what this is doing, this is making it so that I don't have too many parameters I'm estimating. And this will make it so that, so basically we're not running hypothesis testing on any of these, but I'm going ahead and I printed these out just so that you can see what's going on. And you'll notice that the confidence intervals are literally just the estimated value. They have width 0 for the confidence intervals. So when I'm modeling, if I'm going to be using these estimates in any way, shape, or form, I'm assuming that the measurement is perfectly correct since I have 0 standard error, which probably isn't right. But there's only so far we can go with statistics and data and mathematics. All right, so after looking at the output from ANOVA and from the other structural equation model output, I think maybe we should remove agreeableness 1 and agreeableness from EP and agreeableness 1 from DP. Okay, and so in the structure of this, if I'm doing backwards elimination, which is really what I'm doing, it's okay for me to remove both of them at the same time because I have 2 different equations. If I was, if I had one target variable, one equation, and I was setting it up where I would just be removing, be doing backwards elimination, you really only want to remove one at a time. But since I have two different dependent variables, two different formulas, it's okay to take out one from each on each step. If I was doing backwards elimination, I only want to remove one independent variable from the equation at a time. And so I'm just going to go through, I'm going to refit using the Levon package. Let's see what happens. All right, so it's a little bit simpler of a diagram. Here we can see what the coefficients are, and we can see the modeled values for the covariances. Let's look at the parameters. All right, so everything is statistically significant. All right. None of our confidence intervals are hitting zero. Things overall are pretty much the same as before. Since they're pretty much the same as before, that's a sign that it would have been okay to keep those terms in the model. If I remove a term from a model and the values change radically, that's a sign that it was a good decision to remove it. So here, full model or reduced model will probably give you pretty close results. If things get wildly change, you definitely want the reduced model. If things don't wildly change, then including that non-statistically significant independent variable is probably okay. All right, well, that's all I've got for you. Take care and goodbye.